to talk about the pictorial representations of motion. This includes three things that I want you to know: motion diagrams, dot diagrams, and labeled sketches. Recall that there are only four types of motion: at rest, constant speed, increasing and decreasing speed. We're going to talk about these over and over again. Motion diagrams are visual representations showing direction for velocity and acceleration for a particular situation. While there are an infinite number of situations, there's only four types of motion, and there's only either left, right, up, down, diagonal, so there's a limited number of motion diagrams that you have to be able to draw. Why are they useful and why do I care about them? Well, it's really important to know the signs of velocity and acceleration. And since they're both vectors, the direction that the arrows point will tell you their signs. There are two parts to motion diagrams: showing arrows for the direction of velocity and showing an arrow for the direction of acceleration. You need to know which way the object's moving to show the direction of velocity. And to know the direction of acceleration, you have to know what type of motion it is. So the direction of acceleration is really easy to predict. If it's at rest or constant speed, acceleration is zero. By definition, if you're not moving, you're not accelerating. If you're constant speed, you're not accelerating. So your motion diagram for something at rest is always going to be velocity equals zero, acceleration equals zero. Your motion diagram for constant speed is going to show velocity pointing in whichever direction it's actually moving. Acceleration is zero. It doesn't matter if it's moving to the right, left, up, down, or diagonally. If you're increasing speed, acceleration points in the same direction as the velocity arrows. So if you're moving to the left, velocity is to the left and acceleration is to the left. Moving to the right, velocity is to the right, acceleration is to the right. Down, down. Decreasing speed, acceleration points opposite from velocity. So if velocity is up, acceleration is down. If velocity is to the right, acceleration is to the left. That's decreasing speed. It's very easy to predict. There are only two possible motion diagrams for a freely falling object, because for free fall, either you've just thrown it up and it's moving up with decreasing speed, or you've dropped it or thrown it down and it's increasing speed. That's it. Either velocity's up or velocity's down. No matter what, acceleration is down, because that is the definition of a freely falling object. Acceleration is due to gravity, and gravity always pulls down. Dot diagrams are another way to represent motion, and you'll see these and need to be able to interpret them. So you want to imagine like there's a car and it's letting out a drip of oil every so often, right? At a regular basis, every second, every 5 seconds, whatever it is. So you would be able to trace its path. And if there's a large distance between the dots, that means it's covering a lot of distance in that amount of time. If there's a small distance between the dots, you've covered a little distance in the same amount of time. Therefore, you're moving much more slowly because you didn't get very far. If you want to show constant speed, you have to have equal spacing between the dots. Acceleration is zero. If you're increasing speed, you're going to get the size between the dots is going to get bigger and bigger and bigger. Acceleration is in the same direction as the motion. If you're decreasing spacing between the dots, that means you're slowing down, and your velocity and acceleration point in opposite directions. If you're moving to the right, acceleration's to the left. If you look at these dot diagrams here, which one could possibly be free fall? Well, you're either decreasing on the way up or you're increasing on the way down. This shows constant speed. This shows increasing speed on the way down. This shows increasing speed on the way down. And this shows constant speed. So it could be either B or C. Although, now that I look at it, C is showing pretty constant speed for the second part. So I would say, no, it's not C at all. It's B. The third thing that you need to be able to do with pictorial representations is a labeled sketch. Now, we've talked about this since the beginning of the year, but when we're talking about labeled sketches for kinematics, it is absolutely crucial. You're going to need to be able to identify Where's displacement? Where's your position? Where's your velocity? What's your acceleration? So when you read a word problem, you're going to want to label all of the kinematics quantities. So it's going to be the first part of the problem solving process where you sketch a diagram, right? Make a dot diagram, make a motion diagram. You're going to list all your given information. You're going to identify the unknown. You're going to want to skip these steps, and it's a really bad idea because you need to break down what the word problem's asking for and get it on paper. If you try to retain it in your brain and select your equations based on what you remember, it's much more rife with errors. So we are going to follow this process and develop it when we get to problem solving. So a few cues to remember is when they ask you how long it's going to take, that's time. When you're asking how far something's going to go, that's displacement. When we ask how fast something's moving, well, that's velocity. And when we're talking about the rate of change of speed or the rate at which the velocity changes, that's going to be acceleration. The units will help greatly. Please make sure you commit those to memory. So a man is driving at a speed of 20 meters per second when he sees a vehicle in the road ahead. He immediately applies the brakes and it decelerates at 7.5 meters per second squared. How far does he travel before coming to a stop? So I'm going to draw this, and excuse my drawing because I'm not very good at doing this on the computer. So here's my car, and what I'm going to do is I'm going to list my variables, right? I'm moving on the x-axis, so I'm going to do x, v, x, t for the beginning and the end. Now what defines beginning and end? I do, or the problem does. The beginning is the beginning of the situation. The end is the end of the situation. You can call this V1 and V2, V initial and V final, whatever makes you happy. I'm going to do 1 and 2. Initially, they say the car is driving at 20 meters per second. Meters per second is a unit of velocity. So I'm going to put that here. He immediately applies the brakes and decelerates at 7.5 meters per second squared. That's an acceleration. So that's between two things. So acceleration is always in between. So I'm going to label that here, 7.5 meters per second squared. And then how far does he travel? That means I need x2. I want to know how far I went. So I'm going to call the beginning here 0. So I'll find out how far he went. We also always start our time at time is 0. And we're coming to a stop, which means velocity at the end is 0. So now I've labeled all of this information. I also know that I'm slowing down. So velocity goes to the right. We're moving in this direction. But since we're coming to a stop, that's decreasing speed and accelerations to the left. If I make my positive direction to the right, that means that my acceleration must be negative. So these are the signs that I have to use. So you can actually write it in here, and you can leave the velocity positive since that's what it is. And so this is a completed sketch for the problem solving process. Let's do one more like this. A ball is dropped out of a 10-meter high window. What is the total time it takes the ball to reach ground level? So here's the ball at the beginning. Here's the ball at the end. I always label V, but now not X because I'm working vertically. I'm going to call this Y. So these are my positions. VYT here and VYT at the end. So this is my initial time. Time equals 0. Let's call this 1. And it's dropped, and we talked about in free fall when we use the word dropped, it means velocity is 0. And I know I'm 10 meters high. That's where I'm starting. We don't know how fast you're going at the end. We'll call this V2. Y2 is ground level, which I'm going to call 0 meters. And time 2, we don't know. This is what I'm looking for. This is the unknown. I generally just put a question mark in for it. Acceleration is always between the two velocities. And in this case, since we're in free fall, we know acceleration is due to gravity. Notice that that's not something that's stated. You have to know that from the context of the problem. The other things we need to do is I'm going to show, oh, sorry about that wiggle, here that my positive is pointing up. That's my axis. So when I talk about Y position here and here, this is my origin, right? And this is the 10 meters up. I can also draw a motion diagram. I am moving down, that's the direction of motion, and I'm increasing speed. I know acceleration points down because it's acceleration due to gravity. Both of these are negative because I made positive up. So I'm going to make sure to put my little negative sign here and check this is a positive number because I'm above 0, so my position is positive and I don't have any values for my velocity. But if I was going to be solving for velocity, it would end up being a negative number. So that's where we're going to stop for now. You're going to go practice this.